All right, this is the second video of the Chapter 8, Engineering 250. Um, the second video will be talking about special case for the friction. And the special case we're going to cover is going to be the wedge. We're going to skip the 8.5, which is about the belt. We will just focus on the wedge. So first is that what is a wage? Well, the wage usually is used to apply a small force so we can lift a big weight. And sometimes you have a so-called self-locking system. If you use a wedge such as this big wheel and you have a wedge at the bottom, you can stop this big wheel from turning because of the friction between the wedge and also between the object that you are lifting. So this is a very wild applied things that we use, and we wanted to understand in this situation how do we analyze the force, how do we analyze the friction. It all depends on the friction between the wedge and the object. So as you can see, the application of this, then if you put a small wedge at this big wheel over here, and this one normally is very heavy, the friction between the two interface will stop it from turning, and also the wedge and the ground will stop this wedge from sliding, and therefore you can use that to fix an object. What we wanted to do is that how can we describe this kind of a situation? How do we analyze the force between each one of them? And it turns out the most important thing is that you need to be able to understand the free body diagram for each one of the object. So over here, you can see the picture that we have a wedge stop a big weight, and this big weight over here is actually against a wall. So there's two contact surfaces. One is on the right, and the other one is in between the wedge and the object. We're going to ignore the weight of the wedge because normally the wedge is a smaller object and you are lifting a big weight. So we're going to ignore the weight of the small one. When you apply a force to the right, and this one will push in between this big object and the ground, and we are using the friction in between and the friction between the wedge and the ground to stop from moving. So when you push in, you are making these things try to move to the right. The friction should go to the left. So if you make a free body diagram of this object, which is this picture over here, you can see when you push in, the intended motion is going to the right, so friction has to go to the left. And you remember you have friction on both sides. One is on the top between the object and the wedge, and the other one is between the wedge and the ground. You're going to have a normal force. The normal force is going to be perpendicular to the contact surfaces. So these two, the M1 and 2, are both the normal force. However, their direction is slightly different. It depends on the angle, which is the angle of how this wedge incline angle is. So this is kind of how the slope of the wedge, the theta over here. The most important thing again is to have a clear picture of the free body diagram. If we look on the object, the big object itself, this is the big object. You have two contact surfaces. One is on the right, one is in between the wedge. So on the right, you also have a normal force. So now we have N1, N2, and N3. And you also have a friction between the wall and also the object. Now think about the direction of the friction. This object tends to move down. However, the wedge, when you push it in, you are lifting this one up. Because you're lifting this one up, so the intended motion of the object is going up, the friction is going down. And this small things, the wedge is push into the right, so on the wedge itself, the friction goes to the left. But for the big object, the friction goes to the right because they are action and reaction. Okay, so we have a much clearer picture of the free body diagram for both things. Then we can just use the summation fx, summation fy, and also the friction force equation to help us to solve the problem. And let's look at how we solve these problems in the next slide. So over here, we just wanted to let you see both of the objects. So this is the wedge, and this is the free body diagram of the wedge. On the right hand side is the object you try to lift, and we're only concerned about the weight of this object. We're not considering about the weight on this one here. And you have how many unknown that you have? You have on this one, you have 1, 2, 3, 4, 5. On this one, you have 1, 2, 3, 4, 5 as well. Now M2 and N2 are the same over here. F2 and F2, they are the same as well. So take out 2 of them. So you have in total like 10, and you take out, so you have the P, you have the M1, M2, M3, you have F1 and F2, F3. So you have in total 1, 2, 3, 4, 5, 6, 7, 7 of them, right? Now each one of the friction is going to be related to the coefficient. It's going to be equal to the mu s times the whatever the normal force that against that. So then you have 3 friction, however you're going to get 3 equations. And then we need to, there's another way as well, right? Then we need to use the summation f of x, summation f of y for each one of the cases. So this one you have one summation fx, summation of y. This one you have another summation fx, summation of y. So each one is going to give you 2 equations. Then you have 4 equations plus these 3. Then you have 7 equations. So let's see 1, 2, 3, 4, 5, 6, 7. You do have a unknown, but normally you will be given with some kind of a weight or some kind of push force. So so then you can solve the problem. There's an idea called a self-locking, which means if we don't push this one, once you slide this wedge in and remove this force here, it will be locked. It would be locked was simply because of the friction force prevented from moving, and that is what we call the self-locking. On the belt analysis, it's talk about a belt around a wheel, and normally the belt just like a rope, and supposedly the tension in the rope should be the same. And if there's one side of the force that is greater than the other side of the force, and you must have a slip, right? You will have a slip, and the slip will have some friction in between them, and there's some kind of equation. We're going to skip this part here. It's a little bit more complicated, so we're going to skip the belt analysis. We're going to look at the wedge. We're going to focus on this one. Here we're going to give you an example. So you are given with load, which is 3,000 pounds, and which is this one here. And the load is applied to the B block, and which is another wedge. And the coefficient of the static friction between A and C, which is between the bottom A, the wedge, and the ground. So this one have a mu sub S is equal to 0.3. And you have a friction between B and D, which is this one here, is also like the wall and also the wedge. This one is also equal to 0.3. And between A and B, which is between these two wedge, and this one is equal to 0.4. And we want to find out what's the smaller force needed to lift this one here, which means you are going to assume the friction force is going to be the maximum static friction, because beyond that you are start to lift it, you start to make it move. So the friction force will be all equal to mu S times m, and these m will be depends on what surfaces they are looking at. So let's draw the free body diagram for each one of the block, so the A block and the B block. If you look at the wedge of A, you have a normal force from the ground, friction force between ground and the wedge, friction force between two wedges, and normal force that push from the top, the push force P here, which is something that we try to find. On the second part, which is the top wedge, you have a load from the top, 3,000 pounds. You have a normal force between the block, and these two are going to be the same because they are action and friction and reaction. Friction force is going to be the same, which is going to be this n is not Newton. This n is actually the normal force right here. Okay, and this two friction force will be on the opposite direction because they are action and friction. On the wall, you also have a friction force, so this is also 0.3 times whatever the normal force, which is n sub d. So there's two, so the key is really the free body diagram. You have to draw a correct free body diagram in order to analyze the situation. Let's count how many unknowns we have. We have n, we have MC, we have MD. MD is the wall and the wedge of B. We have push force, which is the one that we try to solve. And what else? We're going to ignore the weight of both of the wedge. And this pretty much is what you need to solve. You have four unknowns in this two block. You can simply use summation F, summation Y to find for each one of the case to get a solution. So we apply equilibrium equation to wedge of the B, which is this one here. Let's see what we have. We define X and Y like this. If we look at the Y direction, this is the Y direction. And in the Y direction, we have this one here. This is the Y direction. In the Y direction, we also have this one here. We have part of this. We have part of this, right? So you have 3,000 right here, minus 0.3 n times d, yes. And then we need to find a component of the n in the y direction, which will be the sine, because the angle is 15 degrees, so you have n sine 15 degrees. For the friction, it will be similar, except that for the friction, you look at this angle here, this will be 15 degrees as well. And we are using the cosine because this will be the adjacent component, which will be n times cosine 15. If you look at the x direction, so let's look at the x direction. The x direction, we have component from this one here. Let's use this one. Okay, so this is this is MD in x direction, and we have component from here. We have component from here. So you have three components. This is a minus MD. And for the n over here, the y component will be x component will be the x component will be the sine of that, right? So sine 15 degree, that's for the n component. For the friction, then you have y direction, x direction should be the cosine of that. Yeah, so it's cosine 15 degree for this friction force here. So you have two equations, and over here we only have n and md. Then you can solve this part, and you solve n and md, which are these two numbers right here. After that, we use the wedge of A, and we do the same thing. We look at summation f of y. If you look at this one here in summation f of y, this you have mc, you have component from here, you come component from here, and that is mc going up, and you're gonna minus this normal force coming down with some components. So which is this one here, and cosine 15 degree, because this is going to be the adjacent part right here. And then you have the friction force here, and the y component will be the sine 15 degree, and it will be 0.5 times the n, so that is your y direction. For the x direction, and you have p, you have this 0.3 mc, you have component from here, you have component from here, you have four items here. So p right here goes to the right. The 0.3 NC, we solved NC in the previous one, and this 4485 is the normal force on the top, and you're gonna have a sine 15 degree, and this one is the friction force times the cosine 15 degree, and then we can solve the problem. So you got MC and P. So the minimum force is 4,054 pounds, and that is how we solve this problem. So it's very simple. There's no moment at all. You just need to find the force for each one of the case. So to summarize this one, if you want to make a more general case, this is just a picture to show you if you have two block of the wedge, and one is at the bottom and one is on the top. The L represent the one will be lifted, and consider about all possible situation. You can write the equation, and that is the key thing that you need to learn for the wedge. This will be the chapter 8, and we will talk about more example in the lecture.